Hello everyone. Welcome to this training session on estimates and sample sizes. My name is Vamsidhar. As a part of this session, let's focus on a few aspects relating to estimations. We would try to do the following estimations. So in this session, let's focus on four types of estimation. If I want to estimate what would be the population proportion, which is very commonly used for some kind of scenarios like what percentage of votes can a particular political party get, or what is the proportion of males in a particular population. Anything to do with the proportion estimation, I'll use this kind of a mechanism. Proportion of a population, probably where population is not available, but using a sample, if I want to estimate the proportion of a population, I can depend on this particular mechanism. Similarly, if I want to estimate the mean of a population, under two scenarios. In some cases where the standard deviation or a variance of the population is known, how do I estimate the mean of that population from the sample? How do I estimate the mean of the population from the sample in case the standard deviation or the variance of the population is unknown? And the fourth mechanism which we will deal in this chapter is how do I estimate the variance of the population. So there are three key aspects in a population we are estimating here. One, we would be estimating the means of the population. Two, the proportions in a population. And three, the variances or the standard deviations. And remember, all these we are estimating because we don't know the entire population. We cannot do the calculations on the entire population because of either unavailability or the hugeness of the population data. So we depend on a sample, and based on the sample calculation, we are trying to approximate the population's mean, proportion and variance using the concept of central limit theorem, which we have discussed in our earlier chapters. That's the typical way to estimate any of these various population parameters. Let's go one by one. Let's start off with the population proportion estimation. Whenever we talk about a population proportion, as I just discussed, I'll take a sample, find out the proportion of the sample, and based on some kind of manipulation to that sample's proportion, I will estimate a population proportion. And a few key things to understand in this is, from the sample proportion, it's very easy to estimate the population proportion. That has been proven through various theories. So if at all I have to estimate a population proportion, the good point to start with, the first basic point to start with is start with a sample proportion, which means take a sample of data, and that's what will give me a question, what should be the size of the sample, which we will deal with it slightly in the next slide. But the sample whatever we are taking, find the proportion of a particular value in that sample, which means if I want to find out what proportion of seats will a particular political party XYZ get in the upcoming elections, or what is the proportion of the votes that that particular party will get in a particular constituency. If I want such kind of an analysis, obviously I cannot go to each voter and find out to which party he has voted. So the roundabout way or the workaround for me there is take a sample probably of some people, let's say 1000, How do I determine this? We'll come to know. But let's say I'm starting with 1000. For this 1000 people, I'll find out, I'll interview these 1000 people, I'll find out how many of them have voted for XYZ political party. So let's say if I get that 300 of these people have voted for the XYZ political party. So the sample proportion in this case for me is 300 out of 1000. So I'll start with 30% as the base. 30% is the sample proportion, and that's the base estimate. That is what is called as a point estimate. Point estimate is one single dotted value which will be used as a base for estimating the population value. And generally this is one sample, and some other sample, if I had taken some other 1000 people, probably I would have got 31.5. So what happens is, for the different samples which I am taking, the proportion could be different. If that's the case, which number would be the population number? And that is where, instead of considering a point estimate, people think of considering a confidence interval estimate. So if I have got 30% here, find out the plus or minus level here. And so say that this is the possible population parameter. This is the population proportion which is very much possible. So using the point estimate, build some kind of confidence interval around that point estimate, which will tell you that this particular interval with some level of confidence, will typically contain the population parameter. So if I say that this is the interval, I can say with 95% confidence that whatever is the population proportion I am talking of will lie within this interval. There is only a 5% chance that this interval does not contain the population proportion. There is a 95% confidence or guarantee that the population proportion lies within this interval itself. You should not say that there is a 95% chance of the population proportion lying in this interval. This interval contains the population proportion, and I can assure a 95% chance to it, because population proportion is a fixed value. Whether our interval is able to capture that population proportion or not is the question here. So I should say the 95% chance that this particular confidence interval which I am building around the point estimate contains the population parameter. So that is what is the process that is done. So when I say confidence level of 95%, it means if I try various samples and I consider a confidence interval, there is a 95% chance that this particular confidence interval which I am building will contain the population parameter. Let's look at this. So whenever we use the word confidence level, we always talk about a percentage. The most common percentages are 90% confidence level, 95% confidence level, and 99% confidence level. So it is represented with a term called 1 minus alpha. If I say 1 minus alpha is 95%, it means alpha is equal to 5%, and this alpha is called as level of significance. So one more word, or significance level is what is another word that is used. Confidence level is 1 minus alpha, and alpha means significance level. So whenever we talk about a particular confidence interval, so if I say 95% confidence interval, what it means is whatever the interval which you have built, there is a 95% confidence that this interval contains your population parameter, assuming that this process is repeated large number of times. You should never use this statement, because statistically you should make proper statements also. It's not that there is a 95% chance that P will, the proportion will lie in your confidence interval. You should not say it the other way, because P is fixed. That proportion for a population is fixed. What you are saying is, whatever your estimate you are giving, I'm 95% sure about my estimate. Your estimate could be deviating from the actual value. So you are building a confidence interval which says, I'm 95% confident that whatever the estimate interval which I am building, it will contain the population interval, population parameter, which is population proportion. Right? So that's the important point you have to remember in case of estimations, because at any point in time, the proportion is fixed. Population proportion is fixed. What you have constructed as a part of your confidence interval may or may not contain it, which means there could be some error in your interval construction mechanism. But it's not the value of the population that is deviating. The proportion of the population is always constant. Your mechanism which you have used to create an interval may be deviating from what the actual value is. So that's how we have to interpret the confidence interval. And I can compare two confidence intervals. Let's say the first data set, the confidence interval is this, and the second data set, the confidence interval is this. What we are saying is, I'm 95% sure that the population proportion, that this particular interval contains the population proportion. Here I am saying I am 95% sure that this particular interval contains the population proportion. Now I cannot make any conclusion, because there could be a possibility that the population proportion could be here for this data and it could be here for this data. Then it means the proportion here is greater than here. Or it could very well be possible that in this case the population proportion is here, in this case it is here. Then I am saying population proportion of the second data is greater than that of the first. Now if there is any kind of overlap in between the two confidence intervals, I cannot say that the population proportion of one is greater than that of the other. 2 points for us to remember. If I have to say, make a statement, the population proportion of one data set is greater than that of the other, I need to have two exclusively non-overlapping confidence intervals. But that does not mean if they are overlapping, I can say that the population proportions are equal. The converse is not true. If the intervals are not overlapping, I can very confidently say that the proportion of one of the populations is greater than or less than that of the other. Whereas if they are overlapping, I cannot make any kind of conclusions. Okay, now coming on to the concept of critical values, because to build the interval, to build a confidence interval, 95% interval or 99% interval, to build some level of a confidence interval, one of the important data sets that we require is the critical values about the data. We have also discussed in our previous chapter, critical value is nothing but that particular value on the x-axis, or that particular z value that will create an area to our requirement. That will create the area under the normal distribution curve to our requirement. So if I want a 95% area under the curve, which means if I am 95% confidence level, it means I need a 95% area under the normal distribution curve. So that 95% could be like equal from both the sides. Symmetrical 95%, which means I have to eliminate 2.5% on the left hand side and eliminate 2.5% on the right hand side. I want that corresponding values here and here. And for this I can refer to either a normal distribution tables. We'll have normal distribution tables. You can check out for what is the area under the curve right from the left. What is that proportion which will give me, and if I am looking at from the normal distribution tables, I should always look at what is the point that will separate the area to our liking right from the left. If I want to omit 2.5% on the right, I have to check out for what is that particular point that will create an area equal to 97.5%. So I will get the value as 1.96. Similarly, if I have to check out from the normal distribution tables, the one that eliminates 2.5% on the left hand side, I will check out what is that particular value of Z where the area is equal to 2.5%. So that will come out as minus 1.96. Now using these two, I'll say that the critical value is minus 1.96 and plus 1.96 if I am looking at 95% confidence interval. Similarly, if I am looking at 90% for a normal distribution, you can remember these values straightforward. For a 90% confidence interval, I say that the critical values are minus 1.645 and plus 1.645. For a 95% confidence interval, they are minus 1.96 and plus 1.96. And for a 99%, it is minus 2.58 to plus 2.58. So any value, when I say it separates that particular area in the right tail of the standard normal distribution. So when I say I want 5%, I want to find out what is that particular area on the right hand side. So from that standpoint, I'll check out the normal distribution tables, and based on that I will arrive at the corresponding Z values. So at least what you can see is, in case we are talking about the standard normal distribution, and we are talking about 90% or 95% or 99% confidence level, I can very well take these particular values 1.645, 1.96 and 2.58 being the critical values for that. Then how do I use these critical values? Along with the critical values, I also depend on one more thing called the margin of error, or sometimes people call it as the standard error. What it says is, it's a maximum likely difference with a probability of 1 minus alpha, which means with a confidence level of 95%, I can say that the maximum likely difference between the observed proportion of the sample and the population, with 95% confidence, I can say that the error between the observed sample values and the population value is this much. That is what we call as the margin of error or the standard of error or maximum error of the estimate. So what we generally do is, whenever we are calculating whenever we are trying to build the interval, we'll first take the critical value based on whether we are interested in 95% interval or 90% interval or 99% interval, and multiply it with the standard error or margin of error. Whenever we are talking about a population proportion, the margin of error is calculated by this formula. because the proportions are assumed to follow a kind of binomial distribution, we go with this formula. The proportion of the population multiplied by Q, which is 1 minus P, proportion which is not in the population, which is like success into failure divided by N. Everything is under the square root. This is what we call as the margin of error. Depending on the confidence interval which we are talking of, this particular value, this is called as a standard error, and this standard error, when it is multiplied by the corresponding critical value, we call it as a margin of error. And what we do as a part of our estimation process is, whatever the sample we got, whatever the sample proportion we got, let's say 30% is what I have got by doing the sample. I'll say 30% minus whatever is the margin of error, which is, let's say if I am going with 95% confidence interval, then I am saying 1.96 is the critical value, multiplied by, if I have observed 30% is the proportion, then I'll say 0.3 into 0.7, because which is a failure part is 1 minus P, which is 0.7. And let's say my data contains 84 samples. If I have done this entire thing using 84 samples, so N I am taking it as 84. So what is coming out? 0.3 into 0.7, which is 0.21 divided by 84. Or on simplification, it is becoming 24 and 21 divided by 8400, which is making it square root of 1 by 400, and which comes out as 1 by 20. So the margin of error is 1.96 into 1 by 20. So which comes out as 0.196 by 2, which works out as 0.0098. 0.009 or 0.098. I'm sorry. 0.098. So how we are using this margin of error is, we have got our proportion to be 30%. Now what I'll do is 30% minus 9.8%, 0.098 is around 9.8%, and I'll say 30% plus 9.8%. So overall I'll say my 95% confidence interval is 20.2% to 39.8%. So what is that we are concluding from here? There is a 95% confidence that the population proportion lies between 20.2% to 39.8, or I can simply say the interval which I have built, I am 95% confident that this interval will definitely contain the population proportion. And in this case, some of the things we have to be comfortable, because the proportions internally are using binomial distribution, because PQ, when I am taking the proportions, they are as equivalent to success and failure corresponding to a binomial distribution. So all the conditions of the binomial distribution need to be satisfied, like the experiment is repeated n number of times, all the repetitions are independent in nature, I can classify everything as only two outcomes, success and failure. If I am talking about voting for a particular party, vote for that party is a success, no vote for that particular party is treated as a failure. As simple as it. Then at least there should be 5 successes and 5 failures, which means that the entire thing is going even with the criteria of NP greater than or equal to 5 and NQ greater than or equal to 5. Only when such condition is satisfied, then I can build a confidence interval of this kind. And one thing we have to be clear in estimation of the population variance is never make a statement saying that the proportion is unreliable because we are using a very small sample size. Because population size is never a factor in determining the reliability of a proportion. We'll see what sample size to be used, but never ever make a statement that the proportion values are unreliable if the sample size is very, very small, because the population size is not a factor in determining the reliability of a proportion. And how do I determine the appropriate sample size? This is a very good equation. If I know the sample proportion, like in my earlier example, I said sample proportion is 30%. If I know the sample proportion, then this should be your minimum sample size, which is Z, which is the critical value square. Let's say I'm going with 95% level of confidence. So 1.96 squared into P, which is 0.3, we know the proportion, into Q, which is 0.7, 1 minus P. Yeah, and E talks about the margin of error. How much of margin of error you are looking at? Let's say if I want 2% error, not more than that. If my margin of error needs to be only 2%, what I'll do is I'll put 0.02 whole squared. If my error has to be only 2%, margin of error, then I'll put it as point. This is the desired margin of error, which I am taking it as 0.02. Never take it as 2, because I want a 2% margin of error. Never take it as 2. If you take it as 2, then it becomes 200%. So take it always as 0.02. Do it as a square. So whatever the number that comes up, this round it up to the higher side and say that is the minimum sample size you would like to go with. And in case you don't know the initial estimate of the sample proportion, before knowing the sample proportion itself, you want to find out what should be the appropriate sample size. Then what it says is you assume the sample proportion to be 0.5, which means 0.5 into 0.5, 1.96 squared into 0.5 into 0.5 divided by 0.02 squared. So that's where you'll see this part. In case you don't know the sample proportion, you will directly go with 0.25 itself. This is one of the mechanisms which you can use, especially when you are doing an estimation of a proportion. The moment you know the population, the sample proportion, and you are clear on the margin of error. If you want only 1% error, divided by 0.01 squared, which means you need a very big sample size. So you have to really balance between what is the kind of margin of error you can allow for and the accuracy, because the margin of error, if it is much lesser, you have to obviously go for a very high sample size. And sometimes instead of simply going with a proportion, a population, a sample proportion plus or minus the Z times the standard error root PQ by N. This was what is the mechanism which we have used to estimate the confidence interval. 95%, 99%, something like that. But there is one more advanced formula that has been come up, which is called as a Wilson score confidence interval, which is a much better estimate compared to this simpler estimate of the confidence interval. So probably whatever is the population proportion you have got, use the Z square, Z 1.96 squared, N being the sample size. So you can substitute all these values, and based on that you can create a 95% confidence interval. In reality, this particular formula is reflecting the true population to a large consistency compared to our initial base formula. So that's one more thing we have to keep in mind. The moment we program these kind of things as a part of some of the tools like Excel or SPSS, we can directly start using the confidence interval from this kind of a mechanism. So in a nutshell, if I want to estimate the population proportion, we are starting off with a sample proportion, and around that sample proportion we have to build a confidence interval. To build a confidence interval, we need two things. One is the critical value corresponding to what level of confidence we want to build the interval, and two, what is the margin of error that is allowed, which is basically coming from the standard error. And in case of proportion, the standard error is given by root pq by n, and based on that we can always compute the margin of error, and adjust your sample proportion with the margin of error on both sides, and say that this is the 95% confidence interval. The 95% confidence interval means there is a 95% chance that whatever the interval that I have built contains the population proportion. And to execute this entire activity, obviously we require a sample size. So I have to find out what is an appropriate sample size, and that appropriate sample size is coming out by the mechanism which are shown in the formulas here, based on what level of confidence I am expecting, and based on whether my sample proportion is known or not known, and what is my desired level of margin of error, I will decide my sample size. And finally, we have even discussed about the Wilson score confidence interval, which is a slight modification of the base confidence interval formula, which is reflecting the proximity to the population proportion compared to the base formula which has been used. Now, the next thing we would be looking at is the estimation of the population mean. Right? Even if, for example, if I want to find out what is the average height of an Indian male, so because I need the average, and I cannot go to every Indian and try to find out his height, so I will again depend on a sample, and based on the sample I have to make a conclusion or make an interval about a particular population. That is what is the process. So to start with a base, which is like a point estimate, sample mean is a good base to start with. So take a sample of some size, right? How do you measure what is the sample size? Here we are seeing at the bottom. Take again the z value, which is the critical value. So for example, if I say 1.96, 95% confidence interval, so take a z value, and whatever is the standard deviation of the population, if I say standard deviation of the population is 5%, take that, and your desired scope of error, let's say 2% is my desired scope of error, take that and do an entire whole square, and whatever is the final value you are getting, that is what is boiling down to the sample size that is appropriate. All right. Now, some of the things, some of the points to be kept in mind while building your confidence interval. First of all, the sample should be a simple random sample, which means voluntary responses and all will give you biased results. So always make sure that the sample which you are collecting is a simple random sample, and you should know the population standard deviation. If you don't know the population standard deviation, we'll come out with another form of estimation, right, which we'll look at a couple of slides later. But if you know the population variance or a standard deviation, then only this particular mechanism is applicable. And you should make sure that your data is following one of these two rules. It is satisfying one of these two conditions. Either your whole data is normally distributed, then don't bother about what is the size. If the data is normally distributed, you don't need to bother about the size of the data. And in case the data is not normally distributed, at least the sample size should be 30. If both the conditions are not met, then you cannot estimate the population mean through this mechanism. And as we have discussed for a proportion, the first thing I have to do is find out the sample mean and then build an interval around it. To build an interval, in case of proportion also, we have used two things. One is the confidence interval corresponding the critical value. So, and the second is the margin of error, which contains the standard error. So, in case of population mean estimation, the critical value will still remain the same. If I am going for 95% confidence interval, then plus or minus 1.96 will become my critical values. Whereas the standard deviation or standard error is given by sigma by root n. Sigma is the standard deviation of the population divided by square root of n. There we have used root pq by n in case of proportions, whereas in case of mean estimation, we use sigma by root n. So our margin of error directly becomes the z times sigma by root n, the confidence interval corresponding critical value times sigma by root n, which means our confidence interval comes out as whatever is the sample mean minus that margin of error, whatever is the sample mean plus the margin of error. For example, I got a sample mean as 160. When I am trying to find out the average height of an Indian male, let's say I got the average height from a sample mean as 160, and the standard deviation, let's say I have got it as 4000 or 400, wherein I have taken a sample size of 400 people. A sample size of 400 people or sample size of 400 people, if I am taking, let's say the standard deviation of that entire sample has come out to be, of the entire population, let's say the standard deviation is around 400. Then by using sigma by root n, I am saying 400 by root 400, which is 20. I am saying that the standard error is 20. And if I want 95% confidence interval, then I am multiplying the critical value with 20, which is what is giving me probably 39.2. And if I am building a 95% confidence interval, then I am saying 160 minus 39.2 to 160 plus 39.2. So what I am saying is between in the interval 121.8 or 120.8 to 199.2 is the interval which I can say with 95% confidence is the typical height of an average height of an Indian male. That is what we are trying to use when we know the standard deviation of the population. Either I can build an interval for the average or the mean, or I can also decide on what is the approximate sample size which has to be taken for getting similar kind of result with this much of error scope. Then, in case we don't know the population mean, or in case we don't know the population standard deviation, if sigma is unknown, in the earlier case when we know the sigma, we have used the procedure relating to the normal distribution, and we have built the interval based on the same way which we have built for a population proportion. But in case the standard deviation of the population is not known, then we are resorting to another distribution. We cannot use the Z distribution or the standard normal distribution. In that case, we have to resort to something called as the t distribution instead of the normal distribution. What it says is, it looks more similar to your normal distribution. In your normal distribution, we were using x bar minus mu by sigma by root n. Because if I am not having the normal distribution, then I am finding out, if I am not having the population variance, I will find out the variance from the sample itself and then use it directly. So the S by root n, S is the mechanism, or S is the a formula for sample standard deviation. And what is typically observed is the t distribution also looks more similar to a normal distribution, but a few things is it is slightly wider than the normal distribution, which means for getting your 95% area under the t distribution, the values will be slightly wider. Instead of 1.96 as a critical value for a normal distribution, here you may find a critical value to be around 2.1 or 2.2, because the t distribution is slightly more wider compared to a normal distribution. And it's also observed that t distribution will keep differing in shape based on what is called as the degrees of freedom, which is nothing but it is the shape of the t distribution is heavily based on the sample size. Degrees of freedom is nothing but, let's say if I have a sample mean of 20 for 20 different values, a sample size of 20, let's say it has resulted in a sample mean of 20, then 19 values out of this 20, they can be varied in whatever manner they want, but the 20th value has to be adjusted to create a mean of 20. Because if the 20th value is also random in nature, then overall mean may not be equal to 20. So the 19 values can be any of them, but because the sample value is sample mean is 20, the 20th observation has to be adjusted so that the mean of that particular sample is created to be 20 itself, which means only 19 values are free to be random in this data. That is what we call as the degrees of freedom. How many values out of the given sample size can be free to be modified, and at the same time your sample value is kept intact, sample parameter is kept intact. That is what we are calling as the degrees of freedom. And for all examples pertaining to the estimation of the mean, we can very well take the degrees of freedom to be n minus 1 based on the sample size. If the sample size is 20, the degrees of freedom will be 19, and so on. Now, how do I use this information to estimate the confidence interval? The same process. Find a point estimate. Point estimate is nothing but the sample mean itself. Then build a confidence interval around the mean. And for building a confidence interval around the mean, we require two things. One, the critical value, which will talk about the level of confidence, 95% or 99% level of confidence. So the critical value in this case cannot be based on a standard normal distribution, especially when the sigma is not known. It has to be based on a t distribution. So corresponding to the t distribution, which depends on degrees of freedom, I will try to find out the critical value. So I cannot be 1.96 directly. I have to find out the critical value assuming the data is following a t distribution, not a normal distribution, and finding out the 95% area under that curve. And then I need a margin of error, which is again derived from the standard error, which is more or less the same as in case of the earlier. We have used sigma by root n there as the standard error. Here we are using s by root n because we don't have sigma here. We are calculating the standard deviation from the sample because we don't have the standard deviation of the population readily available. So your margin of error is whatever is the t value that you are getting multiplied by the standard error, and this is what we are calling as margin of error. And what we do for estimating our confidence interval is whatever is the sample mean that you have got, you do a minus of this and you do a plus to this, and these are the two values that correspond to your area, which is exactly the same as your previous case, but with the only difference that we will use s instead of sigma, which means we'll determine the standard deviation from the sample instead of the population, and we would also be using the t value rather than the z value, because the z is appropriate only if either my population variance is known and the data forms a normal distribution or the sample size is greater than 30. So here if the population variance is not known and rest of the things are the same, it should be a sample from a normally distributed population, or if it is not a normally distributed population, then the sample size should be greater than 30 itself, and the conclusions are the same. If two confidence intervals are not at all overlapping, then I can very well say that one is greater than the other. The population mean of one of them is greater than the population mean of the other. But if there is some level of overlap in the confidence intervals, then I cannot say that the population mean of one data set is greater or lesser or equal to the population mean of the other data set. Only when there is a difference in the no overlapping at all in the complete interval, then only a definite conclusion can be made. So always remember that point. Then what is this t distribution? Look at this shape here. If I look at this blue line, which is called as normal distribution, we see this red and orange lines corresponding to a t distribution. And what we are seeing is the t distribution is slightly less peaked compared to normal distribution. The shape is changing with the degrees of freedom. So this is the one if the sample size is 12. The red one is corresponding with where the sample size is 12. The orange one is corresponding to a standard distribution and sample size of 3. And what we are observing is as the sample size is increasing, the t distribution is coming very, very close to the normal distribution. So if the sample size is very, very small, then the t distribution values can be very much different from the normal distribution critical values. And what we are also seeing is the tails are slightly fatter. The orange line is above the blue line, even the red line is above the blue line. So what we observe is the standard normal compared to a standard normal distribution, the t distribution will be slightly less peaked and even having more tail. So that is the reason the critical value for a t distribution will be slightly higher compared to a standard normal distribution, and the shape will differ per different sample sizes. That is what we have seen. But some of the good things or some of the overlapping things between the t and the normal is standard normal also has a mean of 0 and a t distribution also has a mean of 0. And in case of standard normal distribution, we say that the standard deviation is always equal to 1, whereas in case of t distribution it is very much different for different sample sizes, and it can be greater than 1. It is greater than 1, and only when the sample size is increasing we observe that the t distribution approximates to the standard normal distribution. So some of the similarities are bell shape, mean being 0, all but very much slightly wider compared to a normal distribution, which means the critical values also will be slightly higher compared to a typical standard normal distribution. When should you use Z? When should you use T? And when are these two methods not useful? One thing you have to see is if sigma is known, which means population variance or standard deviation is known, then I'll definitely go for a normal distribution only. If the sigma is not known, population or standard deviation is not known, and I'm forced to determine the standard deviation from the sample itself, then for determining the critical values and all, I have to depend on the T distribution. But these two, normal or T, the differentiation between normal or T is only under this situation. But both of them require this particular condition, one of these two conditions to be satisfied. Either my whole data should be normally distributed or the sample size should be greater than 30. At least one of these two conditions need to be met. Either for using a T distribution or for using a Z distribution. One of these two conditions are mandatory. If both the conditions are failing, which means if the data is not normally distributed, if the population is not normally distributed, and even the size is less than 30, which means 20 or something, the sample size is 20 or something, then I cannot use either Z or T. We'll discuss about different non-parametric methods in this case. So the non-parametric distributions will come into picture. This is one important slide you have to remember for the usage of normal or T distributions for estimating the sample means. And I want to decide the sample size. The sample size is determined whether it is the T or Z. The sample size is determined exactly in this manner itself. What is the sample size? Z, instead of Z, here I will use T value. And the sigma is something which I don't know here. The sigma is something which I don't know here, but the error, the desired margin of error is known. So how do I deal with? I know the T value. If I want 95% level of confidence, I can find out the T value. And the margin of error is also known. If I want 2% margin of error, I can put 0.02 there. But the only thing that I don't know is the sigma. Because the entire usage of T distribution is under the fact that sigma is not known. If I don't know sigma, especially only for the purpose of calculating the sample size, some of the desired things that were suggested is, one, use the range rule of thumb, which is nothing but range by 4. You approximate that value to be equal to sigma. Whatever is the range, maximum minus minimum value, divide by 4, and you approximate that to be sigma. That's one way you use the sigma there. Or from your sample, just take first few data values, find the sample standard deviation, and then use that to be your sigma for the population for finding out how many, what is the sample size you would like to collect. Or if there are any other studies that have been conducted on a similar kind of stuff, whatever the sigma they have used, you can very well use that particular sigma. But one suggested thing is, in the construction of your sample size, any error you are looking at, be more and more conservative. Don't say that I want only 0.05% error. It becomes very, very tough because you may end up collecting a very huge sample size. So you have to really balance between the sample size which you are going ahead with and the error which you can allow, because if your margin of error goes lesser and lesser, there is a big burden in terms of collecting a big sample size, which means you are incurring heavy costs and various other stuff. So there should be a balance between the range of accuracy and the sample size which you are looking at. right? That's one important point you have to keep in mind. Never look at very small value of very small value of the margin of error, because that brings additional pressure in terms of collecting a huge sample size to make your interval determination, to make your estimation. Then one more thing that we are looking in this particular chapter is estimation of the variance of the population. So till now we have looked at estimating the population proportion, and then estimating the population mean in case the sigma is known versus sigma is not known. In case I want to estimate the variance or standard deviation in the population, we will resort to something called as chi-square distribution. If you remember from our previous chapter, the sampling distribution of the means is following a normal distribution. Sampling distribution of the proportions will follow a normal distribution, whereas the sampling distribution of the variances will follow a skewed distribution to the right. That skewed distribution to the right is called as a chi-square distribution. Even that chi-square distribution depends on the sample size, which means the degrees of freedom. If the sample size is n, then n minus 1 will form the degrees of freedom, as we have discussed in case of t distribution. The chi-squared value comes out as n minus 1 times s squared, which is the sample variance, divided by the sigma squared, which is the population variance. This particular equation will follow a chi-square distribution. Some of the things which we are looking with respect to chi-square, it is not symmetric, and what we are seeing is the shape is differing with different degrees of freedom, which means with different sample sizes. It is not symmetric, it is looking more skewed to the right. And what we are observing is, as the sample size is increasing, 20, 25, 30, some level of normality is coming into the data. As the number of degrees of freedom increases, the chi-square distribution is approximating to a normal kind of a distribution. So symmetry comes only with a higher size in the data, and the critical value is again based on the degrees of freedom itself. Just like we talked about the critical value, the definition of the critical value remains to be the same, right? It simply says that particular separating value which will give the desired area under that particular distribution curve. So because this distribution is a chi-square, I want to have a 95% interval here, probably 2.5% to the left of it and 2.5% to the right of it. I want to find out these two lines which will constitute the 2.5% on both sides. That is what is my are my critical values in this case. The mean is not 0, both in t as well as in z distribution we had means to be 0, whereas in chi-square the mean is not 0 and it is skewed, which means and also we are observing that there cannot be any negative values. Chi-square is always positive. Even when I do this kind of a calculation, n is the sample size, so n minus 1 is always a positive, or worst case is 0. S square, which is the variance, chi-square is also the sigma square is also a variance. Variances are always positive terms, so this entire chi-square value can never be negative. The worst case it could be 0 and it can never be negative. So these are some of the things that we have to understand using the chi-square distribution. And again, if I am using the chi-square distribution to estimate the population variance, small difference here is, again I require the margin of error as well as the critical value. And what we are saying here is, the critical value I am computing as n minus 1 into s squared divided by chi r squared, which means whatever is this part of the area, that is what is given my chi r squared. And if I am talking about which is the right area, so 2.5% in the right right of that curve, whatever is the area corresponding to it, whatever is the x-axis value, chi-square value corresponding to it, and similarly I am talking about chi-square L, which is this particular value. What is this particular value of the x-axis where the area to the left side of it is equal to 2.5%. So based on these two values, I am trying to adjust the so I'm doing a calculation of n minus 1 s squared by chi r squared, n minus 1 s squared by chi l squared, and say that my population variance, the interval for my population variance is this, which means I am 95% confident that whatever the interval I am defining contains the population variance. And a few of the things that need to be satisfied even for this estimation: the sample should be a simple random sample, and the population should have normally distributed values. If the population does not have normally distributed values, we cannot use this chi-squared mechanism also. So remember, the moment you remember these kind of formulas, it's not that difficult to build confidence intervals. And once you have built this confidence interval successfully, they will be helpful in terms of making statements also, like, okay, the variance cannot be more than 30%. Because if your 95% interval comes out to be 18% to 28%, then you can make a statement, I'm 95% confident that it cannot be 30%, because your 95% confidence interval is 18% to 28% for the variance. So a statement of 30%, you can very well reject that statement at 95% level of confidence. And that is what you making a claim about a statement is what is the context of our next chapter, which deals with hypothesis testing. But in this chapter, you should be comfortable with the building of the confidence intervals, one for a proportion, one for means given the population variance, or means without the population variance, and also you should be comfortable in building the interval around the variance. I hope you're comfortable with these four types of calculations once you listen to this session. If you have any further queries, I suggest that you feel free to call me on the number here. You can even drop in an email to me explaining your doubt to this email address, vamsidhar@pacegurus.com. I request you to visit our website www.pacegurus.com to get continuous updates on training and consulting activities done by us in the areas of finance, investment, statistics, and analytics using tools like Excel, VBA, and SPSS. I hope this session will give you a complete clarity in understanding the various estimation mechanisms and various mechanisms to determine the appropriate sample size for estimating the appropriate parameters. Thanks a lot for listening to this session. Thank you very much.